chapter 8, there are about 5 major concepts that are going to include basically everything we cover. And the first 2, especially the first one, are just going to be sort of conceptual type questions. But the other 3 are going to primarily be problems. But you need to know the concepts well enough that you can then do the problems if they ask you some information that will allow you to know something about the concept to understand it. So we'll start with physical versus chemical changes. This is the shortest idea from chapter 8. This is just the idea that there's 2 different ways to identify, to talk about, and describe a change that occurs. It can be chemical. In a chemical change, that means something is going to change by the way the atoms are bonded together in our system. For example, if we take water and we do hydrolysis to turn it into hydrogen and oxygen gas, now the hydrogen and oxygen are bonded differently, even though we have the same numbers of hydrogens, oxygens at the beginning and at the end. In a physical change, though, we're not going to get a change in the chemical bonding. For example, if I crush a can of aluminum, it's still aluminum atoms, they're still bonded the same way, it's just in a different shape. Or, for example, we could take water and boil it. The water is still going to be water molecules with one oxygen bonded to 2 hydrogens, whether it's a liquid or a gas. So that'll still be a physical change. That's really all you've got to get with is be able to identify something as either a physical or chemical change. The second category was the idea of reactants and products, and this is primarily so that you can do the other questions. Just make sure you know what I mean by these terms. Reactants are going to be the materials that we start out with. These are the things that we're going to bring together to react in some way, to somehow change how they're structured. And products are going to be what we get at the end. Once our reactants come together and they rearrange in some way, now we have products. This allows me to talk about things like the reactants and the products when I'm doing a question about one of the other concepts, and you should be able to identify, oh, you said reactants, that means the stuff we started with, versus products, that's the stuff we got at the end. For example, I could do a limiting reactant problem, and I could ask you what would be the mass of the products at the end. And you would need to know that that meant that the products were the things you got at the end, not the stuff you started with. So if I asked that question, I would have not said the mass of the products at the end. I would have just said, what is the mass of the products based on this reaction? So you need to know that products are the things you get there. Now we have 3 other categories that I'll talk about just a little bit, but most of it will be when we actually go do examples on the next slides. First was the idea of balancing chemical equations. This is the idea that just because we have all the same atoms on each side doesn't mean we're yet a true chemical equation. It needs to be what we call balanced. That means that if I start with 2 hydrogen atoms on the left, I better end with 2 on the right. If they're not balanced, that means that's not how the chemical reaction would actually occur. Because for us to have this reaction, we have to have enough of the atoms that we can get the stuff we have at the end, but we can't have any left over. If we have something left over, then there's some product missing from our equation. So we need to make sure that in the end for our chemical reaction, that we see that the very beginning and the very end have the same number of atoms when we add them all together. Then we have the idea of mole-to-mole conversions. This was simply the idea that now that I have a chemical equation and it's balanced, I can figure out from, let's say I start with 3 moles of a particular reactant. I can use that chemical equation to figure out how many moles of a product I would get from those 3 moles of reactants. We'll get that through specific examples where we can either just start with moles or we can actually also start with grams. And then we can go to moles like we did back in chapter either 5 or 6. Then finally we have the idea of a limiting reactant problem. This will be similar to some of our mole-to-mole conversions and balancing chemical equation questions, but now we ask an additional question. What material do you run out of first? The idea being, if I just take some hydrogen and some oxygen together to try to make water, and I don't make sure it's exactly the right amounts of each, it may turn out that I have more hydrogen than I need, so that I run out of oxygen, and some of the hydrogen stays unreacted. We have to be able to identify those things. In general, if a problem doesn't tell you something like you have exactly the right amount, or that one of the materials is in excess, but instead gives you how much you have of 2 or more of the reactants, then you probably have a limiting reactant problem. And at the very least, you should go through the steps to make sure you know which one you would run out of first. If it turns out you actually had exactly enough, it's no harm to have done a limiting reactant portion of the problem and figure out, oh, we had exactly enough. Because if you forget that step and that's not true, your answer isn't going to work out very well because it's not going to make sense because you're not going to actually have enough to use up all the reactants even though you assume that you did. So let's go to some example questions now to look at what these look like. So first we're going to start with just balancing chemical equations. How do we do this? So what we're going to do is I'm going to write off to the right. I suggest you write below for these, but I don't have room right here. So in our first example, we have H2 plus O2 goes to, that's the way to read that arrow. The idea is that means you're reacting. So the stuff on the left is reactant. Then when you get to the right, that's the stuff that's your product. So in this problem, we have hydrogens and oxygens. On the reactant side, we have 2 hydrogens and 2 oxygens. On the product side, we have 2 hydrogens and 1 oxygen. So now we need to try to make these numbers the same, because of balanced chemical equations, the left and right will have the same numbers. So I'm going to start by trying to change the number of waters I have. Because I have 1 oxygen on the right and 2 on the left, clearly I need more oxygens for my water. I can't put a half in front of my O2. So I'm going to put a 2 here. That is going to change my oxygens to 2. But it's also going to change my hydrogens. We have to take into account everything that changes. We now have 4 hydrogens. From here, I can now go over to the left side and say, oh, we have too few hydrogens. Let's make it so there are 2 of these here. That will give me a total of 4 hydrogens and 2 oxygens on both the left and the right, giving me a balanced chemical equation of 2 hydrogen molecules plus 1 oxygen molecule makes 2 water molecules. That's our balanced chemical equation. So let's try a second one now. Let's try our Na2CO3 plus hydrochloric acid goes to NaCl plus H2CO3. So now we're going to have to balance that we have sodiums, we have hydrogens, we've got chlorines, and we also have carbons and oxygens. Note that you can do the CO3 together because it's a polyatomic ion. The reason I separate it out, though, is because sometimes you'll only have the polyatomic ion on one side, and the other side it'll break up. For example, in certain reactions, you'll break this CO3 and you'll end up forming some carbon dioxide plus something else that uses the rest of the oxygen. And then it would matter. If you're comfortable with doing it, though, where you do the polyatomic, as long as you're sure it's the same on both sides, it's also fine to balance the CO3s together. But it's not going to make the problem much harder to do it this way, so I like doing it the way where we separate it, because that works in all cases rather than just some. So, on the left, we have 2 sodiums, we have 1 hydrogen, 1 chlorine, 1 carbon, 3 oxygens. On the right, we have 1 sodium, 2 hydrogens, 1 chlorine, 1 carbon, 3 oxygens. So, we don't have any atoms by themselves, and all the atoms only appear in 1 molecule on each side, so we just can start wherever. There's nothing special to do. So I'm going to start with the one I wrote first, with my sodiums. So you'll notice there's 2 on the left and 1 on the right, so I am going to need to make it so there are 2 sodiums on the right. To do that, I need 2 sodium chlorides. That will also give me 2 chlorines. Next, I'm going to go to my hydrogen. My hydrogen only has 1 on the left, but 2 on the right. So I'm going to make it so there are 2 HCl's. This will give me 2 hydrogens and 2 chlorines. Now, we have the same number of carbons and oxygens, sodiums, hydrogens, and chlorines. We've got a balanced chemical equation. Even though there were 5 atoms, it turned out we only needed to put 2 coefficients in front of anything. So sometimes you'll have something with a lot of atoms, but it won't have very big numbers. And other times, even if you have very few atoms, you may end up with a whole lot of stuff there. So you can't take for granted the fact that, oh, this many atoms means it's going to be a whole bunch of stuff I have to do. Sometimes they'll be easy, sometimes not so much. Okay, so let's try our third balancing. For this third one, we have aluminum, copper, sulfur, and oxygen. So on the left, we have 1 aluminum at the start, 1 copper, 1 sulfur, 4 oxygens. And on the right, we have 2 aluminums, 1 copper, 3 sulfurs, and 12 oxygens. Now remember, you'll notice that at first view, okay, the coppers and the aluminums are by themselves, so I'm going to try not to mess with those at first. I'm instead going to go to my sulfur first, because I know I can easily adjust the aluminum and copper at the end. So if I go to my sulfurs, because those are part of 2 compounds and neither are by themselves, you'll notice the left I have 1 sulfur, but the right I have 3. So I'm going to put a 3 in front of my copper sulfate, and that is going to give me on the left 3 coppers, 3 sulfurs, and 12 oxygens. You'll notice both the sulfurs and oxygens are now balanced, so now we can do the atoms that are by themselves. So I go to the aluminum, and I want to make this a 2, so I'm going to need 2 aluminums on the left, and then I want to adjust my copper, which is by itself on the right, and I'm going to need 3 of those. So that's going to give me 3 coppers. So the balanced chemical equation of 2 aluminums plus 3 copper sulfates goes to 3 copper plus our aluminum sulfate. So not too bad, but it helps if you remember to do your sulfur and oxygen first, since my aluminum and copper were by themselves. So let's do one last thing. Let's look at a combustion reaction. Here we have methane, which is going to be carbon and hydrogen, plus oxygen. It's going to go to carbon dioxide plus water. So we'll note we have 1 carbon at the start, 4 hydrogens and 2 oxygens. And on the right, we have 1 carbon, we have 2 hydrogens, and we have 3 oxygens. So at the start, I'm not going to do oxygen because it's by itself on the left, and it's in two different compounds on the right. So it's going to be my hardest to do, so I'm going to leave it till the end. So we're going to start with, okay, the carbons look fine at the start. We won't worry about those. Now we've got the hydrogens. Well, in the hydrogens, there are 4 hydrogens on the left, but 2 on the right. So I'm going to need 2 water molecules. That is going to bring me up to 4 hydrogens. Now we go down 1 below, because we've still got our carbons are fine. And our oxygens, though, are now equal to 2, 3. We've got 4 oxygens. That was a step I almost forgot. Don't forget you have to change both your hydrogen and your oxygen when you put a coefficient in front of the water. So now we have 4 oxygens on the right, 2 on the left. We put a 2 in front of the O2, and this brings us to 4 oxygens. You'll note, if you had tried to do this problem the other way, where you started with the oxygen, you would have had 2 on the left and 3 on the right, and you would have had to do something different, and it probably would have made the problem look a lot more complicated than it was. You probably would have put 3 oxygens on the left, and then you would have doubled everything on the right so that you had 2 carbon dioxides and 2 waters, and then you would have had to do a bunch more balancing, and the problem would have turned out a lot more difficult than if you just started with something that wasn't the oxygen, which is why we suggest to consider what molecules would be what atoms would be the simplest to do when we're trying to choose what to balance first. Okay, so these are some fairly straightforward balanced chemical equations. Let's look at some stuff now where we've got to do something with these balanced chemical equations. So we're going to look at some mole-to-mole calculations. So these first couple are intentionally just in moles because we're not going to worry about the grams, conversions, and all that yet. We just want to look at, if I've got how many moles on one side, how many do I get on the other? So this is also before we worry about limiting reactant, because I'm going to tell you what you have in excess. So for each of these examples, let's start with the first one. It's already balanced for you. You can even check, though, if you want, and make sure that the number of aluminums and number of chlorines turn out the same, which they do. So you have 2 aluminums plus 3 chlorines goes to 2 aluminum chlorides on the right. You'll notice that we tell you you have 12 moles of chlorine and you have excess aluminum. So we've got to convert from moles of chlorine to moles of aluminum chloride. We note this because the problem asked us to find out the moles of the underlined compound, and it's aluminum chloride that's underlined here. So we're going to write our starting material, which is 12 moles of chlorine. We are then going to convert this now into aluminum chloride. You'll note that there will be 3 moles of chlorine on the bottom because we want our moles of chlorine to cancel. And that for every 3 moles of chlorine we have, according to our balanced chemical equation up above, there would be 2 moles of AlCl3. You'll notice the moles of chlorine do indeed cancel. We get 12 times 2, which is 24, and then we divide that by 3, which is going to be equal to 8. So we are going to have 8 moles of aluminum chloride, AlCl3. So that's our first one. Let's do another. Here, in the second problem, we have the question of if 2 nitrogen NOs plus 5 H2s combines to form 2 NH3s plus 2 waters, what do you get if you have 20 moles of hydrogen at the start but excess NO? And it specifically underlines the NH3, so we don't have to worry about how many waters we make. So let's check this out. We start off with 20 moles of H2. Now we want to convert from moles of H2 to moles of ammonia. So we know that there are 5 moles of H2 for every 2 moles of ammonia, or NH3. You'll notice the moles of H2 cancel again. And we get 20 times 2, which is 40, divided by 5, which will again give us 8 moles of NH3. So we've got one more to do. We have P4, which is phosphorus, plus 6 Cl2s goes to 4 PCl3s. And we're told we have 6 moles of P4 and excess chlorine. So let's try doing one more of these. So here, if we start with 6 moles of P4, and we convert, and we know that for every 1 mole of P4, there are 4 moles of PCl3 in our balanced chemical equation. And that'll give us 6 times 4, which will give us 24 moles of PCl3. You'll notice I don't think any of these 3 questions were all that challenging. I understand that. But what's important is that you be able to recognize this right away and do this quickly, because this should not be a step that takes a long time. You'll notice when you look back at my old exam, there were a couple of questions like this, and I hope you can do them very quickly. But we also could combine this, right? You could have to balance the equation first, and then use it to try to find this equation to find out how many moles you have. Or, as we'll look on the next slide, we'll start to have more information. For example, we could have limiting reactants, or we could start in grams or need to know how many grams we're going to get. So this step right here needs to be very comfortable for you. At the same time, I also don't want you to look at this and think there's some trick to it and think that, oh my gosh, this seems too easy. There's got to be some other step. I've seen students do that where they'll, because they're so used to doing the more complicated problems, where they'll get to this question and they'll try to convert things into grams and then into molecules or something because they're not sure what to do, because it's actually simpler than a lot of the questions they've been doing. So let's go to our next slide. Now we're going to have an issue of a limiting reactant. This is where we've got how much we have of two different materials, and we've got to figure out what we run out of. So we're going to start with our first equation, which has aluminum and chlorine going to form aluminum chloride. We're told we have 12 moles of Cl2, and we're told that we have 7 moles of aluminum. And we've got to figure out how much AlCl3 we're going to make. So remember, we first have to start by figuring out which is our limiting reactant. So we're going to take each of these and convert them into AlCl3 and see which makes the least. So we know that for every 3 moles of chlorine, we're going to get 2 moles of AlCl3. And we did this back on the last slide, so this one shouldn't be too bad. This should still give you 8 moles of AlCl3. But now we also have to look at the aluminum to see which one we're going to run out of first. And here we know that we have 2 moles of aluminum for every 2 moles of aluminum chloride. And we'll notice from this that we would actually get 7 moles of AlCl3. So we are only going to make 7 moles of aluminum chloride because when we do this, we'll run out of materials before we can make our 8 moles of aluminum chloride. Now, there's one other question I'm just going to do it with this one rather than the other 3, but I want you to think about for a second. Let's say I'd added another step to this question. What if I asked you, how much chlorine are you going to have left over in this question? I want you to give that a shot for a second. So I'd suggest you pause real quick and give it a try and see what you get. Okay, at this point, you've either come back from a pause or you've decided, yeah, I'm not doing that. I'm just going to listen to you because I don't feel like doing it. Either way, it's fine. So let's consider what we need to do. We know that we're going to be able to make 7 moles of aluminum chloride. So we need to figure out how much of our 12 moles of chlorine we're going to use up. So I'm going to go ahead and erase this part. So we're going to make a total of 7 moles of aluminum chloride. No. I can't find this pen's eraser, so I just marked it out. So what you'll note is we've got to figure out how much chlorine we used up. We can go backwards just like we went forward. I can figure out, based on what my product was, how much of the reactants I should have used up. So for every 2 moles of aluminum chloride, we are going to use up 3 moles of chlorine. And for this, let me get my calculator. We have 7 times 3 divided by 2. We are going to use up 10.5 moles of our chlorine. You'll note that we started with 12, so that means that my 12 minus 10.5 is going to be equal to, well, if I had written this question with this in mind, I would have written it as 12.0 moles in the question. So I would have gone up here and I actually would have written 12.0 and 7.0. That way our sig figs would work out well, or in this case, our decimal places. So let's assume I did it like that. If we had 12.0 minus 10.5, we would then get that there are 1.5 moles of chlorine left over. You'll note that I think when I show it this way, and at least I've seen it with students in office hours, this made a lot of sense to them once they try that out. They go, oh, right, that's how much is left over. But it's recognizing that you need to take how much product you made and then go backwards and figure out how much you used up. And then compare that to what you started with to figure out that is usually the hard logic step for people to get. So make sure you can recognize that and that feels okay, even if I'm not next to you telling you, oh, don't forget, you can take your product and then go backwards and figure out how much you used up to help you figure out your excess. So let's try the other 2, and for these, because there's the extra grams to mole step, I'm just going to do the limiting reactant part. But if you'd like to have more practice at it, I strongly encourage you to do 2 more questions, the next 2, where you try it out with, okay, how much of my excess reactant do I have left over? It's good practice. So here, we'll use the same equation we used on the other page as well, with our NO plus hydrogen going to NH3 plus water. So we're told that we have 11.0 grams of NO. And I'm going to go ahead and figure out how many moles of this are and then how much NH3 I can make. So my nitrogen, 14.01 plus 16.00, So we know that our NO is going to have a molar mass of 30.01 grams of NO per 1 mole of NO. Now what I'm going to do is I'm going to keep writing this problem out like I do sometimes in class, but if you need to do it as 2 separate steps, that's perfectly fine. We also know that I can get of moles to NO 2 moles of ammonia. So I know that for every 2 moles of NO, we are going to get 2 moles of ammonia. Notice the moles of NO cancel, the grams of NO cancel, and so that will work out. And this would tell us that we would get 11 divided by 30.01, that we're going to get, and then times 2 divided by 2 is just 1 for that. So we are going to get 0.37 moles of NH3. Also, this is because I only had 2 sig figs in my question, but if you were to go on to do more, I suggest using more numbers from your calculator than this to do future calculations, and just do this type of rounding at the end. So now we've got to compare this to our hydrogen. So we have 8.0 grams of H2. We know that for every 2.02 grams of H2, we're going to get 1 mole of H2. From here, we're now going to know that for every 5 moles of H2, we can make 2 moles of NH3. And again, if we go and check, our grams of H2 cancel, our moles of H2 cancel. So we get 8 divided by 2.02 times 2 divided by 5. We get that this could make, let's see, 1.6 moles of NH3. Clearly, our limiting reactant is our NO. So if it asked you to specifically write the limiting reactant, you would say it was NO. And then we would box our answer of 0.37 moles of NH3. Because clearly we run out of NO much sooner than we run out of hydrogen, even though there are fewer grams of hydrogen. Because you'll notice the hydrogen has a smaller mass. So that's one way that can happen. So remember, don't just look at I've got 11 of grams of one and 8 grams of the other. Clearly the 8 grams runs out first, because I see some people that try to do that when solving the questions quickly. You have to actually go through and figure out in moles and then take into account what the ratios are in your balanced chemical equation. Let's try the third one. So here we have ammonia and carbon dioxide. So what we're going to do is we're going to start with our 6.0 grams of ammonia, or NH3. We're going to convert that in that 17.04 grams of NH3 is going to make 1 mole. We are then going to convert from our every 2 moles of NH3 is going to make 1 mole of CH4 N2O. And if we go through, we see, yes, grams of NH3 cancel, moles of NH3 cancel. You'll notice I'm always writing out what compound it is. Since there are 4 different compounds in the problem, I strongly encourage you to actually write that out. I see plenty of people that will do like 6 times 1 over 17.04 without putting any units. And then at the end, you can forget, and you accidentally flip around what your limiting reactant is because you don't remember what you started in. So we do this, and we get that we would be able to generate, again, this is a 2 sig fig type problem, how I wrote it, so this would be 0.18 moles of CH4 N2O. Okay, so now let's do it for the other. We have 9 grams of CO2, and we know there's going to be 44.01 grams of CO2 per 1 mole of CO2. And then we can convert, this one just uses a 1-to-1 ratio, so 1 mole of CO2 makes 1 mole of CH4 N2O. Moles cancel, grams cancel, we're left with moles of CH4 N2O. So we get 9 divided by 44.01 times 1 a couple times, and we're going to get that we would have 0.20 moles of CH4 N2O. So again, so this time our NH3 is going to be our limiting reactant. We can box that one. Okay. So hopefully, one thing also to consider is that if you needed to, you could also convert this back to grams, right? So I could have instead asked for how many grams you would get and not just how many moles. And then you would have taken your 0.18 moles of CH4N2O. You would find out what the molar mass of CH4N2O is by looking up the molar masses of carbon, hydrogen, nitrogen, and oxygen. And then you would simply use the same type of conversion that we used in this step that I'm circling now. Except now the unit, it would end up being slightly different looking, but otherwise it's a step like that, right? We can go from grams to moles or moles to grams. You should be able to do both very comfortably because you're going to do this a lot in this exam. You've probably already noticed. Okay, so I wrote one additional question. I added another question here because I realized we didn't have one that used quite as many words. So if this wasn't on the review, the version I gave you, so I'd suggest you look at this for a moment and give it a shot. That means pause if you actually try it. Okay, so the question is that ammonia is produced using the Haber process. 3 hydrogen molecules plus a nitrogen molecule makes 2 NH3 molecules. What is the percent yield of ammonia that is produced from 14 kilograms each of hydrogen and nitrogen if 12.7 kilograms of product is recovered? Assume the reaction goes to completion. You'll notice this is an example of where some of those words I mentioned are important, things like knowing what a product is, being able to recognize stuff. So the first part to note is that this first sentence doesn't matter at all. Ammonia is produced using the Haber process. That is nice information. It is true, that's what it's called, but that's not going to affect our problem. Being able to figure out information that just doesn't matter can help us out with these problems, especially if you look at my last exam, I had a problem that had like 8 sentences. It's being able to figure out which parts are important and which aren't. Now this clearly matters. This is our balanced chemical equation. And we can check and it matches out. There are 6 hydrogens on the left and 2 nitrogens, and the same is true on the right. So check it and make sure it's balanced. Now, we had a question about percent yield. That means I know I'm going to need an actual yield, and I'm going to need to find a theoretical yield. The problem tells me what I start with. So what is produced from? Now remember, so produced is going to be our verb type thing, but we're asking it's produced from something. So that's telling me what the reactants are. That I have 14 kilograms at the start of both hydrogen and nitrogen. You'll notice also this is one thing about paying attention to how sentences are worded. This problem tells you how much hydrogen and nitrogen you both have with just one number, because you have both 14 kilograms of hydrogen at the start and 14.0 kilograms of nitrogen at the start. So make sure you can identify that all right. And then I say if 12.7 kilograms of product is recovered. You'll notice this is where I tell you how much you actually got when you did it. So this is our actual yield. So to figure this out, and we're going to assume the reaction goes to completion. That means I don't have to worry about stuff not working right for the figuring out the maximum amount. So we're going to figure out from the maximum what we should have gotten, and then compare that to the product recovered to figure out what our percent yield was. So we start with 14 kilograms of hydrogen, and we're going to figure out what it can make. So remember, we've got to first convert both of these into grams. So there is 1 kilogram of hydrogen and 1,000 grams of hydrogen. From here, we have that for every 2.02 grams of hydrogen, we're going to get 1 mole of hydrogen. From there, we know that for every 3 moles of hydrogen, there are going to be 2 moles of ammonia. Also, the problem gives you the actual yield in kilograms, so I'm going to suggest that that's what you convert to. So we're going to go that for every 1 mole of ammonia, there's going to be 17.04 grams of ammonia, and that for every 1,000 grams of ammonia, there's going to be 1 kilogram of ammonia. I know this looks like a really long thing, but this is one way to make the problems a lot faster to solve is if you can get comfortable doing these in multiple steps. Because see, look, I just checked the units each time. The kilograms cancel, the grams of hydrogen cancel, the moles of hydrogen cancel, the moles of ammonia cancel, and the grams of ammonia cancel to give me kilograms. And what would have looked like something where you had to write out 1, 2, 3, 4, 5 different steps is now 1 step that's slightly longer. This can help a lot with trying to get done on time. Okay, times 2 divided by 3 times 17.04 divided by 1,000. Okay, so from this, I got that, wow, this hydrogen could make a lot of ammonia. This hydrogen could make 78.7 kilograms of ammonia. Now let's try with the nitrogen. Let's figure out how much we could make from it. So the start is the same. It's still 1 kilogram. Goes to 1,000 grams. Just have a different mass now. We know that for 1 nitrogen, there's going to be 28.02 grams of N2 for every 1 mole of N2. The problem then shows us, if we go back to the balanced chemical equation, that for every 1 mole of N2, there are going to be 2 moles of ammonia produced. And that's supposed to be a 3. Sorry if it got a little squiggle from the hydrogen because I didn't pick up the pen. Now we've got to convert it to grams. And we know back from up above that for every 1 mole of NH3, it's going to be 17.04 grams of NH3. And then we're going to have, and this is why, be careful when you write on your paper, I kind of jam them together right here at the end. For every 1,000 grams of NH3, we're going to get 1 kilogram of NH3. We could go through and we can see the units do still indeed cancel. So we have 14 times 1,000 divided by 28.02 times 2 times 17.04 divided by 1,000. And there we're going to get that we could make a total of 17.0 kilograms of ammonia. That means that my limiting reactant is going to be my nitrogen, and then I can make 17 kilograms. Note that while this is a lot of the problem, we are not yet done. And if you stopped here, you'd probably lose a couple points because you need to finish the question. The last part of the question was, what is the percent yield? So this is just going to be our actual over our theoretical yield. The problem told us our actual yield was 12.7 kilograms. And we found that we could make 17.0 kilograms. Multiply by 100%. And we're going to get that we had a yield of 74.7%. That is our percent yield. So don't forget that last step. Don't want to lose a couple extra points for that. If you can do this question here, I think you're pretty well set for how we've got to do this, other than just make sure you can also balance chemical equations. You'll notice we did limiting reactants. We did mole to mole conversions. We also practiced our grams to moles conversions using molar mass, and our kilograms to grams conversions using our units that we were doing back in the first exam. So this problem includes a lot of different steps. Also, we had to know that a percent yield was an actual yield over a theoretical yield. And we had to be able to read a problem that had a couple sentences in it and be able to figure out from that what the question was and what we were trying to find. So I think this is a good example of what a larger question will look like. There will be a few like this on the exam, and then some of the others will instead be really short steps like balance this chemical equation or convert this one thing from moles of this to moles of that. Because you can only do a few of these. They'll be worth 4 points. There'll be stuff at the back. But the multiple choice will have to be something a bit shorter, or there'll have to be multiple questions about the same problem. Because if you had to do this for every multiple choice question, the exam would take all day. But hopefully this feels all right. One thing I will point out is that as we're covering the Chapter 9 material, or as you're studying that if you're listening to this at a later time, we're going to be able to use all this stuff once we get to molarity as well. Because all that molarity is going to be is where we can go from moles to liters instead of grams to moles or moles to grams. So we'll have a new way to find out how many moles we have. So we can do all these same questions about using mole to mole conversions and limiting reactants, but we'll just start doing the solutions in the next chapter. So hopefully you get comfortable with this. That way you're okay at doing it once it looks a little different, where instead of writing the word grams, we write the word liters or moles.